Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. Having discussed the free and forced vibrations of a typical 2 degree of freedom system, in this lecture we will devote some time to understand what a vibration absorber is all about and how designing this vibration absorber can help us control vibrations, particularly resonant vibrations of a typical vibratory system.
Okay, so this is what is going to look like the response of mass m1 and that of mass m2, and what we observed is that there are two resonances which are going to appear at these two speed ratios, which are expected because there are 2 degrees of freedom. But what is interesting is this position where the mass m1 of the two masses would have its response 0, and that happens when the numerator becomes 0, which actually means that when the speed ratio is equal to square root of 3. That is precisely the location where the amplitude of the parent of the first mass x1 will be equal to 0, and at that instant or at that speed the second mass will also have its amplitude quite small. So, over a range of these frequencies the amplitude is going to be quite small. So, this particular feature is now exploited for the design of vibration absorber, and that is precisely the point of discussion today. So, what we are going to look at is a system, a vibratory system, which we now define as this is our system. This is something which I will call as a primary system or a main vibratory system, having its mass m and stiffness k, subjected to external forcing function. We assume a harmonic excitation to this parent mass, and we have seen that this response x of t would have of course two resonances, but then it would have 0 amplitude somewhere there and another resonance slightly on the right side. But it is this location in frequency where the amplitude of mass m, which is our parent system or a main system, would become 0, and that is many times required. We would like our main vibratory system to have as low amplitude of vibration as possible, and that would happen if we somehow attach this additional or many times called as an auxiliary system to the parent system, which if it is properly tuned, in the sense that if its stiffness and mass properties are properly adjusted, you might get a situation where your parent system or the main mass m would have 0 amplitude of vibration. That is basically the whole philosophy. This 2 degree of freedom system is quite similar to this 2 degree of freedom system which we have discussed, wherein the amplitude are actually turning out to be 0 here, and of course quite low in for the second mass, but the first mass amplitude of vibration can be brought to 0, and this is what we plan to do in designing something called as vibration absorber. Okay, so what we do here, we assume now that our system actually is a simple vibratory system having its spring and mass properties which you can extract from the actual physical system, and this is subjected to a harmonic forcing function or external excitation f of t, and because this system would have its frequency characteristic like this, which means that it will have a resonance frequency somewhere here, and you would argue that if it has a resonance frequency here, which you already know, why don't you operate it here so that the vibration amplitudes are small? Okay, yes, indeed it can be done, but many times in practice you try to design it maybe about 15-20% away, and for some reason during manufacturing or installation the actual frequency might slightly shift and becomes very close to the operating condition, right? So it is quite possible, and therefore this vibration absorber is many times as an afterthought or can be implemented on site when the system is installed. So let us not worry too much about why we are not having its operating speed away from resonance, but supposing that it has to operate at that speed, and somehow we are staring at resonance condition. In that situation, let us look at how we can contain the vibrations and minimize the vibration even if it is vibrating at frequency omega, which is close to the natural frequency omega n of the parent vibratory system. Now, having said this, what we do is we attach an auxiliary system, as we are seeing here in this particular case. This auxiliary system is appropriately designed so that the system, the parent system, the main system has its vibration amplitude 0. Now, obviously the initial response of the parent system or the main system is this. By the moment we attach this additional system to it, the system no more is a single degree of freedom system, obviously, right? So now it turns into a 2 degree of freedom system, just the way we have seen in the previous slide. So this has its own response amplitude and this has its own response. This may be x, and this let me say as x1, okay, both as a function of time. Now, instead of this single resonance, what is going to happen is that the moment I attach this auxiliary system to the main system, the system turns 2 degree of freedom system, and then I do have now 2 natural frequencies and therefore 2 resonances. Okay, so I am replacing one problem with 2 problems, that there are 2 resonances possible because now there are 2 degrees of freedom. However, if my operating speed cannot be changed from here, okay, which means that I have a machinery which operates at a constant speed, which most of the times is the case, right? If your air conditioning system with the condenser unit operating with a fan which is operating at a constant speed, you don't change that speed of the fan, right? So if it operates at a constant speed, at least at its operating speed range, I am spared from large amplitudes of vibration, right? So by attaching an additional auxiliary system to the parent system, I am splitting the original resonance or natural frequency in 2 split natural frequencies. That means there the middle one gets split into 2, and one is omega n1, which is basically the first natural frequency, and this one the second natural frequency. 2 masses, 2 natural frequencies, right? But what is happening is if my operating speed is here, I do not no more have this kind of a resonant condition, okay, of course, as long as I operate in this speed range only, okay. So this is basically the philosophy of designing a vibration absorber, so that at the operating speed which is close to resonance, the vibration amplitudes are contained to a reasonably low level, theoretically 0. Okay, how does that happen? Partly we have already seen that happening in the previous slide here, where we have seen already that because this curve passes through this point, there is a zero amplitude condition there. Okay, let's look at this little more carefully. through the equations. So we now take into account the natural frequency of the main system. So this is our the main natural frequency, square root of k over m, and that itself is the excitation frequency, will it not? Because we are considering a situation where your operating speed is close to the natural frequency, and therefore there are resonant vibrations, which is the reason why you are trying to design a vibration absorber. So we have a situation where the excitation frequency is close to the natural frequency, and that natural frequency is given by square root of k over m. We define this zero frequency deflection as f over k, where f is the magnitude of the excitation force and k is the stiffness of the parent system or a main system. Okay, and that basically is to help us get the non-dimensional curves of response. Okay, then we define uh, another natural frequency, in this case the natural frequency of the attached auxiliary system. Okay, this system is going to be attached to the parent system, and if I consider this to be an individual vibratory system, single degree of freedom vibratory system, before I attach it to this, then its natural frequency is defined as q, which is equal to square root of k1 by m1, because if I considering this as a separate single degree of freedom vibratory system having its own mass and own stiffness, then the natural frequency of this system q is going to be square root of k1 by m. Okay, the moment I attach, there is nothing like p and q separate, both of them together is now a 2 degree of freedom system which will have its own natural frequencies. Okay, so there will be p1 and p2, or omega n1 and omega n2, those two natural frequencies of a 2 degree of freedom system. However, we have here discussed two different systems, one parent system having its own stiffness k and m, and auxiliary system or an attached absorber system whose own stiffness and mass are k1 and m1 respectively. We introduce another important parameter, okay, which is mu, and this mu is the mass ratio and defined as the mass of the auxiliary system to the mass of the main system. So you basically take the ratio of the absorber mass and the original parent system mass m. Okay, now you would realize that this parameter is going to play a very important role in the design of this absorber. Well, with this, if I substitute the assumed solution, again this is so routine that I don't really need to discuss a lot about this. You assume a harmonic response or a solution to this governing equation of motion, which we have already seen in a few slides back, x to be x cos omega t and x1 to be capital X1 cos omega t. Okay, and because the excitation frequency is omega, the response is also at omega. The damping is not there, so therefore I am not including the phase in the assumed solution. If you substitute these assumed solutions in the governing equations, which already we have discussed, then the expression for the response of the main mass turns out to be this, which also we have discussed few slides back. And similarly, the response of this auxiliary system or an absorber system is capital X1, which is also given. So this is capital X1 is given by this expression. Both these expressions are quite similar, except that K1, K2 are now replaced as K and K1. Then there is absolutely no difference here. Now we already know, because we have these expressions and we have assumed this x of t to be f over k, I can non-dimensionalize this particular equation by appropriately arranging that taking k out from this denominator and then using the expression of mass ratio, I can actually get this x non-dimensionalized as x over xst given by this expression. Okay. Now you will realize that because q has been defined like this and p has been defined like this, the p and q will appear in this expression. So you can leisurely see how this can be transformed into this equation. Now that's a simple mathematics which we are not going to deal with here at the moment. But let us look at this expression in more detail. What is this expression telling us? Yes, what can we say about this expression? Can you say something about this expression? It obviously, if you look at the numerator, x will be 0 if the numerator is 0. And when will it be 0? When omega, or I must say when q is equal to omega, and because omega we are considering close to the natural frequency of the parent system, this is equal to p. In effect, it actually means that if I design the absorber, okay, this absorber is quantified or characterized by its own natural frequency q, and this parent system it can be characterized in terms of its natural frequency p. What this equation tells us, okay, is that if you design this vibration absorber with its natural frequency equal to the natural frequency of the parent system, you can expect the amplitude of vibration of the parent system becoming 0. This mathematically is quite obvious from this expression, okay, which means I must somehow manage to get the stiffness and mass together in such a ratio that the value of its natural frequency of the attached absorber equals that of the parent system natural frequency when the absorber was not attached to it. Okay, that's basic philosophy of the design of an undamped vibration absorber. Okay, and ensuring this q is equal to p, that activity is nothing but tuning the vibration absorber so that the parent system vibration amplitude capital X is equal to 0. Okay. Now what happens to the second mass? We have discussed, okay, the capital X, which is the response of the parent system, that is brought to 0. What happens to the second mass, that is the absorber mass? Well, if I do the same changes to this expression of the absorber displacement amplitude by rearranging some of those terms, I get the expression here, quite similar to the first mass vibration response. Okay. Now in this case, obviously there is no way you get the vibration amplitude 0, right? So, and that you have probably seen in the graph that was mentioned here, where the vibration amplitude actually is not 0, it is some low level amplitude, and that amplitude corresponding to the case where omega is equal to p is some small value. Okay. So when it is tuned and when omega is equal to p is equal to q, you can show that this capital X1 over XST, when it is tuned, then it turns out to be like minus k upon k1, isn't it? Because this part will be equal to 0, because when you set omega equal to q equal to p, this term becomes 0, and then you are left with this expression, isn't it? And what is your response of the absorber? We have assumed it to be capital X cos pt, cos omega t, x1. So now if I replace this x1 from the top equation, then it is basically minus of k upon K1 XST. Now I can replace XST. What is XST? That is F by K. Is it not? Cos omega t. And so I can write this as minus F over K1 cos omega t. This is the dynamic response of the, sorry, this is not X, this is X1, I must write. Okay, the response of the absorber, the second system that you are attaching to the primary system. And so, okay, let me write this as little clearly, minus F over K1 cos omega t. Please make a note that it is negative. What does that mean? Well, that graph you show, I mean, you saw that it was all in that range where the parent system changes from negative to positive. Here, this amplitude was negative, if you recall that point, right? That is what it is, right? But the amplitude is then going to be F over K1, and it is going to harmonically oscillate. So the point here is that you are attaching another external system to the parent vibratory system, bringing down the vibration of the parent system to 0 and letting the attached absorber system to vibrate with whatever small amplitude. Okay. If I use this equation, the denominator equal to 0, what will you get? If I plot this x1 upon xst, right, you would get it this way, and then there will be this kind of a response, and likewise. Okay, this is your response of the absorber system. Now these are the two resonant frequencies where the absorber will have large amplitudes, and of course that those are also the frequencies at which the parent system will vibrate with large amplitudes. Now if I solve the denominator equal to 0, which means that x1 will have infinite amplitude theoretically, these are the two natural frequencies, omega n1 and omega n2. In this case this will be like resonant frequencies, and those two frequencies can be obtained by solving the denominator equal to 0, isn't it? That's what we have seen a few slides back when we discussed 2 degree of freedom system. So this equation is also similar to that equation, except that I have replaced some terms here by the mass ratio mu. Okay, now please try to understand here that P is equal to what? Square root of K over M, isn't it? This is the natural frequency of the parent system. What is the natural frequency of the auxiliary system or an absorber system? This is K1 by M1. And what condition have we assumed here? That originally the parent system is having resonance condition at P. So omega is equal to P. Okay, and then we attached and tuned the vibration absorber to match the absorber natural frequency to the parent natural frequency. So therefore, if this condition has been already assumed, then can we say that K over M is equal to K1 over M1? If P is equal to Q, K upon M is equal to K1 upon M1. What does that mean? That means K1 upon K is equal to M1 upon M, which we have already defined as the mass ratio. Okay, so in this expression of denominator, K1 by K is replaced by mu, the mass ratio, and therefore this becomes now the frequency equation and the solution of this frequency equation gives you the two resonant frequencies omega n1, omega n2, or you can also write this simply as omega 1 and omega 2, the two natural frequencies of the 2 degree of freedom system. Okay, and we will be using this equation in the design of this vibration absorber. Design in the sense, this is already designed, right? The moment you match these two natural frequencies, the design is that way over, except for small issues which we will discuss. Is this clear now? Okay, and this is the expression. If you solve this equation, this is what the expression for the two natural frequencies or two resonant frequencies that we get. If you know or use the mass ratio mu, then the two natural frequencies can be easily obtained. Now a small discussion is in store about what role is played by this mu. Okay, so what I am going to show here is the way. So this is omega normalized with respect to, so omega 1 and omega 2, which I get from this equation, is normalized with respect to the natural frequency of the parent system, and then I plot them here. Okay, now by using plus and minus sign, I get obviously two frequencies. So let us assume that I have chosen this mass ratio equal to 0.1. So at this value of mass ratio, I get these two natural frequencies or these two resonant frequencies. One is this, the second one, the lower one of the two is this. Okay, and it is expected because original when there is zero mass ratio, what does that zero mass ratio mean? M1 by M. So that means there is no M, as there is no M1, there is no auxiliary system. So obviously when mu is equal to 0, you have omega n is equal to P, that is your parent system. The moment you attach this absorber system to your parent vibratory system, the moment you attach this auxiliary absorber system, this changes the single degree of freedom into 2 degree of freedom, and then you have these two natural frequencies split. One will have a larger of the two, which is more than the original one. The lower one will be smaller than the original single degree of freedom natural frequency. Okay. Now the question is, what value of mass ratio should I choose? Yes. So supposing if I plot this original resonance plot, okay, I have this natural frequency plot, sorry, post response plot, which is showing resonance here. What I am basically getting is that by attaching the absorber, this is how the system changes, isn't it? Now I was happy that by attaching the absorber, I am sitting here and I can enjoy zero amplitude condition, operating condition, right? But you all know, and from the practical experience, there would be slight deviation in the operating speed. You cannot expect, the load changes, the speed drops, the load reduces, the speed slightly increases. And therefore, if by chance if you go away from this operating condition little far off from this point, then you would be close to the one of the two resonances, isn't it? And usually these differences will not be, this difference will not be significantly large that you can enjoy a long operating speed range. And why is that so? Because if you look at this mu, and you attach a larger m1, that means you attach a larger mass, you know, which causes this mu to be larger, you can definitely enjoy a much wider difference in these two frequencies. So this delta omega would be larger. As you can see, these two frequencies are split, and the difference between the lower one and the upper one is reasonably wide, right? Isn't it? So you can then stretch your legs and have the operating speed to deviate reasonably well. Okay. If you have a smaller mu, which means that a smaller mass was attached, you have an issue here that the gap between the two new resonances reduces, and a slight deviation would cause larger amplitudes the moment you deviate far off from the original operating speed. What is the problem in then selecting larger and a higher value of mu? First thing is that these curves are flattening out. That means any increase in the value of m1 is not going to fetch you a reasonably wide frequency split. Okay. And then number two, which is more important, is nobody would allow you to attach a heavier mass. Nobody will allow you to attach a heavier mass to the parent system, your original vibratory system. Any attachment of mass means it's going to add to the mass of your system, which is definitely not taken lightly, or is not in fact allowed, or people will object to that, and this is not a real correct design. So you would really like to have as small mu as possible, okay, while ensuring a reasonable split and reasonable range of operation around your operating speed omega. Okay. So therefore this mu is actually selected so that you have a reasonable operating speed range, while ensuring that the attached vibration absorber is not heavy enough. Okay. So it should be as light as possible. You can have K designed appropriately, but any mass which you put there is always going to be a problem of a proper design, right? So this is the part that we basically have to keep in mind, that mu is to be kept as small as possible so that the absorber system is not bulky. If you thought that these are all only in theory, this is one example of such vibration absorber actually implemented in one of the skyscraper. This is you all might be knowing Taipei 101 building in Taiwan, and the earthquakes there are commonplace, and the designers wanted to limit the vibrations subjected to such excitations at the base. So what they basically designed and installed a pendulum absorber on some top floors whose design was essentially inspired from these basic vibration fundamentals that we discussed just now. So this pendulum starts oscillating the moment the building starts vibrating at its natural frequency, and the design is perfectly working. It's I would suggest that you see the YouTube videos where the recordings at the actual earthquake cases are available for you to see how this pendulum swings and damps the vibration of the building. The other examples that I would like to discuss here is the setup that we have, couple of setups that we have in the lab. So this particular setup was shown to you some time back, where a beam which is hinged at this point is as such a single degree of freedom vibratory system, with the motor sitting somewhere here, and then there is a spring at the other extreme, essentially simulating a simple single degree of freedom system. So it is supported by a spring at the tip here, and if I rotate this disc which has an unbalance located, it excites this beam, and the forced vibration response of this simple system, you can view that here. Okay, so the beam is oscillating about the hinge on the extreme left, and we have a reflective tape here to enable us to find out what is the speed at which the beam at which the disc with an unbalance is rotating. So you can see currently the rotational speed is close to 200, and we will set it to resonant condition. That means we will set this operation speed, the speed of rotation, to match with the natural frequency of this setup. And you would now see that the amplitudes become very large as the vibrations are going to be reaching a very large value. The moment I bring the speed so if I bring this speed to a smaller value, and then yes, as you can see now, the amplitudes are really becoming very large. It's the speed at which the beam oscillations become very large. So 160 165 is the in revolutions per minute is the speed. Mind you, the motor is operating at much higher speed because there is a gearbox which reduces the speed of the disc. The discs are operating at reasonably low speeds of rotation. Now what we do here is, suppose this system is representing a typical practical vibratory system, and I am supposed to operate it at this speed. I don't have a choice of changing the speed. Then I can still make it work, and with a lot less vibration amplitude, by attaching a small absorber system. So what you now notice is that to this motor and the beam, we have attached a small spring here, and we shall see how attachment of this absorber system brings down the vibration amplitude to a reasonably low level. So again, we bring it to resonance. So I am going to bring the speed again between 160 to 165 or so, so that you can visually see large amplitudes, and the spring is already attached here. The only thing that is missing is the mass. Now we actually did calculations that if this 160 rpm, which is going to be close to 2.7 hertz or so, and the spring stiffness was measured, and for that spring stiffness what should be the mass to be attached, and the mass turned out to be close to 580 or so grams, and then that mass was then attached to the spring. And let's see what happens when an absorber gets attached to this parent system, whether the amplitudes really come down as we expect from theory. So let me see if yeah, here it is. So actually there are stoppers here which limit the vibration of the beam, and one can actually listen to the third sound when it starts hitting the stoppers. Now what you notice that we are attaching a mass carefully calibrated, so that the natural frequency of this attached spring mass, okay, is same as the natural frequency of the parent system, or the operating speed, that is 165. Now you can see that the parent system, which was oscillating vigorously, has been quietened a lot. Okay, again slight vibrations are seen because the speed got back again to a larger value. So the moment you get back to the same speed of operation, you can see that the beam is almost stationary. Hardly any vibrations are noticed. If you maintain the speed same, you can definitely see a significant drop in the amplitude of vibration, which if you compare it with what you saw in the previous slide where it was large oscillations were seen, this definitely is much quieter. As you compare this with what we had and now what we have here. Okay, so this is how we implement this theory that we learned to practice, of course, in a lab environment, but you have seen one practical applications where they have managed to get the vibrations in that building to a very small value. Now another example that we have in the lab is imitating a multi floor building. So this, of course, we cannot go to 101 floors. We have managed to have maybe 3 floors here, one, second and third, and it is mounted on a base which you can see here, and this base is excited by an electrodynamic shaker. So this is a shaker horizontally placed, and that shaker has a piston that oscillates at a given frequency and amplitude. So the base of this whole building is harmonically moved back and forth, and you can set the frequency to match with one of the natural frequency of this setup, so that you can explore whether the vibration absorber work or not. So what we have done is, you can see an arrangement here at the top floor where something similar to what the IIT building has. So it's essentially a pendulum having an effective length which is equal to this, a mass which is bolted here. The length here is properly calibrated. So again, what we do is, because the natural frequency of the pendulum, you can find out what should be the length, so that this is equal to one of the natural frequencies of this multi-floor apparatus, right? So this L, the length at which this mass is connected, is properly calibrated, so that the natural frequency of this pendulum matches with one of the natural frequencies of the system. Now you can see how this actually can bring down the vibration amplitudes. So okay, so this is basically to show you how the pendulum actually acts. It's a simple strip with a mass at the end, and the length properly. So the slot basically helps you to tune the position of the mass, or fix the position of the mass and tune the frequency close to the resonant frequency. So it will be shown that by removing this absorber, the entire building vibrates at its first natural frequency, and then the moment you put this absorber or an auxiliary system, the amplitude can be is actually brought to 0. So by removing this, you can see very clearly how the shaker is shaking the base. It's just like earthquake moving the base of or foundation of the building, and you can see now this entire multi-degree of freedom system is rocking with large amplitudes of vibration. The first fundamental mode is very clearly seen. All the masses or all the floors are moving in the same phase, and now I just put this pendulum, see this pendulum start swinging, and the parent system amplitude quite close to 0. Okay, of course, in the actual building, you must have seen there were dampers, if you recall. Maybe you can have a look at some of the videos on the web. So these are the dampers that you will see there, right? So this is not an undamped vibration absorber, but you do have some dampers there, and there are reasons why we use, or sometimes we'll have to use damping elements. Okay, so this is basically how the vibration absorbers are to be designed to control the vibrations. The basic philosophy there is to design the parameters of the attached absorber system in a way that its natural frequency comes close to the natural frequency of the parent system. Okay, now let us solve a problem just to get a feel of what this design is all about. This example is of an engine, an automotive engine. The crankshaft um, is connected to the flywheel. The engine generates a torque which is given here. So let's go one by one. The engine is connected to a flywheel. The flywheel inertia is 70 kg square meters, whereas the engine itself has a inertia here, IE, uh, is equal to 0.735 kg square meter, whereas this one is comparatively much higher. And the engine is subjected to a torque. So the excitation torque here is 294 Newton meter, okay, at 100 radians per second. So your excitation frequency is 1000 radians per second. That's what has been given, and the amplitude of the excitation torque is 294. Now here we are talking of torsional vibratory system, not a normal linear vibratory system which we have been seeing. So this is nothing but a torsional vibration, to be solved for. So for reducing the torsional vibrations at the operating frequency, an arrangement of torsional vibration absorber is designed. Now that design is shown here. This is your torsional vibration absorber. So it is in the form of it is in the form of a bar. In the center, this particular part is aligned to the axis of this crankshaft, okay, and this is constrained from oscillating about this axis by these 4 springs. So these springs are basically going to resist any oscillatory motion of this bar, okay. So this bar is like in the slots of this engine or an extension of that engine, so that mass, that inertial mass, swings about this axis, okay, and the oscillation of that mass or that link is restrained by 2 springs on either side, okay. So the moment there is an excitation in the torsional sense, the springs will try to resist and bring it back to its original equilibrium position. This is how the absorber is to be designed. The absorber is tuned to the excitation frequency, and you are supposed to design the inertia of the absorber. That means you are supposed to find out what should be the value of mass moment of inertia of this absorber that we should have, and what should be the spring rate of these 4 springs, so that the resonance frequencies are at least 20% away from the excitation frequency. So basically what we are trying to ensure that once you have 2 split torsional natural frequencies or resonance frequencies corresponding to the original operating 1000 radians per second here, this the drop in the first one should be 20% away from the original one, and this upper one should be again 20% above the original 1000 radians per second excitation frequency, so that you have a reasonable frequency range to operate. So that is what the problem statement is, okay. Now if I try to see this particular system similar to what system that we have discussed in the previous slide, I can immediately see that this flywheel inertia is very large, too big, 10 times large, and we have seen in one of the explanation that if the the stiffness ratio or one stiffness is too high or one mass is too high compared to the other one, I can ignore or I can assume this flywheel to be almost like a rigid one. The moment I consider the flywheel to be the rigid one, then this torsional stiffness of the crankshaft connecting the engine to the flywheel can be treated like a spring. Okay, so this is like K, and it is connected to the engine inertia, right? So this engine inertia is nothing but this mass, and for us the primary system is this shaft and the engine. That is our primary system, to which you are connecting an absorber system, and there the absorber is this particular link. So this is the absorber, and this stiffness K1, so let me keep the notations the same and write here as M1. Now M1 is nothing but the inertia of this particular link, and K1 represents the combined stiffness of these 4 springs, which is going to be the the resisting elements for the free torsional motion of the link. So it actually means that this is my primary system and this my absorber system. The absorber system is all shown here. Okay, it's just that that absorber is compactly sitting in the frame of the engine, or it can be an extension of that frame. But basically, by assuming the flywheel to be large and assuming it to be rigid enough, I am making an assumption here that I can treat this particular system as a primary system, and the absorber inside the engine to be a free vibratory system, which is an absorber system. Okay, this is how I convert the actual physical system into its simplified vibratory model. Okay, coming back to our basic vibration analysis. All right. Now the engine torque is 294 Newton meter, and we are supposed to design the absorber. What would you do now to design the vibration absorber? Our basic philosophy is that the vibration natural frequency of the absorber should be same as the natural frequency of the parent system, which is the operating speed. Okay, we are trying to ensure that at that resonance the amplitudes are brought to 0. Now this omega is already given, it operates at 1000 radians per second. So the moment I know that 1000 radians per second is the omega value, which is to be equated to what? The value of kT. Okay, the stiffness of the shaft is also given, no, 7.35 into 10 raised to power 5 Newton meter per radian. That is the stiffness of the shaft, and that is the parent system, right? So it is K over IE. So this is basically the engine inertia. Okay, now so you can find out from this, in fact this is your the natural frequency of the parent system, right? Square root of K over IE, and this P is equal to square root of 7.35 into 10 raised to power 5 and divided by the engine inertia is 0.735. Okay, one can find this out, and that is obviously is close to 1000, is in fact equal to 1000 radians per second. All right, we would be interested in knowing what is the value of, what value of mass ratio should we use. So M1 over M, which in this particular case of torsional vibratory system, instead of mass we always talk of the inertia of the absorber and that of engine. Is it not? Now we do not know that, right? Because we are not still in fact this the absorber's inertia is what we want to find out. So this is not known. What about the engine inertia? Yes, engine inertia is known as 0.735, but I do not know mu. In fact, I would like to know what is mu. So the other way of trying to resolve this is recalling that our frequency equation, of a two mass system. Remember that frequency equation? Yes, here it is. This was our frequency equation. You can either use this or you can use this. We would solve, or we will use this for the sake of convenience. Okay, now what we do, I might as well as use this omega by p as a ratio. Now you may notice that it has been given that the new natural frequencies or new resonance frequencies should be at least 20% away from the excitation frequency. So which actually means that omega 1 expected should be 0.8 times omega, and omega 2 should be 1.2 times omega. And because omega is equal to p, so this is nothing but writing 0.8 times p, and this is 1.2 times p. So what actually happens is that these two ratios, omega 1 by p is equal to 0.8 and omega 2 by p is equal to 1.2. So what I do, 1 plus mu minus 0.8 square and 1 minus 0.8 square minus mu equal to 0. This is the first equation that I have if I choose the lower of the two new natural frequencies. And the second one will be obviously 1 plus mu minus 1.2 square 1 minus 1.2 square minus mu equal to 0. This becomes the second one. So these two equations, if I solve, I get the value of mu. Obviously I can get it from the first itself, I don't need the second one, no. So if you solve this, the value of mu that you get would be 0.202 or so. So you get two different values of mu from by solving these equations. Now which one will you use? They are of course very close, so would not matter a lot, but you know, if they turn out to be reasonably far apart, then you will have to choose which one of the two will you use, right? So which one will you prefer, the bigger one or a smaller one? The bigger one has to be chosen. Why? Because the smaller one, so 0.19 would give you these two different values of the two natural frequencies, and the 0.2 will give you little wider one. The point is, if you design it based on this, if you design it based on this, it will satisfy this higher one, okay, when you are operating at a higher of the two resonances, but it may not suffice for the required value of mu for the lower resonance frequency. So 0.202 is the mass ratio that you have to use, so that it satisfies the requirement of at both the resonances. So therefore, now that I have decided, or I have evaluated the value of mu, which is 0.202, I now have the relationship where IE and the mass ratio are known. IE is already 0.735 and therefore IA can be calculated, okay, and you know that mu is also K1 by K, okay, which means that this is equal to, or basically 0.202 is equal to the value of K1 over K, that K is that of the parent system, which is going to be the torsional stiffness of the shaft, okay, which is 7.35 to the power 5. So from this I can get the stiffness of the absorber. The only problem is this stiffness is representing the total stiffness, which is this stiffness, but the physical construction here, of the absorber is a bit complex that way, not as complex, but it is comprising this particular link which is restrained at the top and here by the springs. Now look at this absorber system as a spring mass system, no? So if you assume the engine to be fixed and the absorber to be swinging against the fixed engine, okay? It's like saying that if this mass is fixed, this is the engine mass, and now I try to figure out the value of Q for the attached absorber system. So now if this link swings by an angle theta here, right, it swings by an angle theta and then it keeps on swinging about this axis, what is its natural frequency Q? We have to come up with a governing equation, right? So again, free body diagram. Now I will use a little simpler shape of this, hinged here, and then there is a spring here, there is a spring here, and all the spring constants are assumed the same, identical springs. Okay, what will happen if I assume clockwise theta and theta double dot? Can I write the governing equation of this torsional vibratory system? Yep, I theta double dot plus, okay, what will that be? If you really look at the Newton's second law, I theta double dot is mass times acceleration equal to all the restoring forces, external forces to that free body, which are in the same direction as that of the acceleration. Now the moment it turns theta positive here, this spring is going to get compressed, this spring is going to get compressed by how much distance? It will depend upon how much is this distance. So now if I assume this distance to be A, now please make a note that this A is already given to you. So if this stiffness is assumed as Ks and all the springs are identical, so they are all Ks here, then what happens? The restoring force acting here against any theta angle, okay, this spring is going to be getting compressed, so it will also apply a restoring force which is going to be how much? Yep, that restoring force is going to be of course proportional to Ks, and how much is the extension in the spring? That is going to be A into theta, the slight tilt, and A is the length, right? So the stretch in the spring or a compression in the spring is going to be A theta. Now this A theta is going to be same here, will be same here, and the extension in these two springs, that is this spring and this spring, so this spring is going to be again although it is getting extended and therefore it gets stretched, it will try to restore its position. So what I am showing here is that this spring is also going to restore its position, the position of the link, and therefore this force is also going to act in the leftward direction or counterclockwise direction. Is that clear? Likewise, you may very clearly see that all the springs are going to generate a counterclockwise restoring force on the link. The moment link tries to turn clockwise, all the four springs are going to try and tilt it back to its original position, and the force value is going to be same, Ks into A theta. Ks is the spring stiffness at all these four contact points, and therefore the force is going to be 4 times Ks into A theta. Combined effect of all the 4 springs can be this much. Now these are all the forces only. So the moments will be multiplied by what? Right? And the most important of all is what is the direction of these? That is counterclockwise, opposite to the theta double dot. So this is how the equation, governing equation of this absorber system will be. So now if I write this as, and now the absorber, we know that the link's inertia, if I call that as IA theta double dot plus 4 Ks, just to keep it different from K and K1, A square theta equal to 0. That's your governing equation. Now if this is the governing equation, what is the value of Q, the natural frequency of the absorber system? It's going to be 4 Ks A square upon IA. What should be the value of Q for the absorber to work? We already know that it should be 1000 radians per second, equal to P or equal to omega. Now if I equate this to square root of 4 Ks, it's not known. A is already given as 0.15. Please see this one, and divided by IA. Now IA, I will be already getting it from here, and that is equal to IE, which is 0.735 times 0.202. Okay, that is the value of IA. And so the only unknown here is the value of the spring stiffness, which I get from here. This is how I design the vibration absorber. Okay, I hope it's not too complicated here, but this is the process that you will follow for finding out the relevant parameters of the vibration absorber. In this case, a torsional vibration absorber to be used in the engine to reduce the twist in the shaft connecting the engine with the flywheel. That is what we should be checking. What will be the amplitude with which this absorber oscillate, because that sometimes can be very useful or important to find. What is the theta of the absorber link? This is that absorber link that I am talking about. You remember what was the expression for x1t? Just flip few slides back. It was f by k1 cos omega t minus, of course I am not using negative sign here, I am interested in the amplitude, f by k1 cos omega t. Now again, if I am interested in only the amplitude, then I can write this as, now in this torsional vibratory case, it is the external torque, okay, the engine torque, that is relevant, upon k1, and k1 in my case is going to be what? Ks, 4 Ks A square, na? Because the effective spring stiffness, torsional stiffness, is going to be 4 times Ks into A square, right, cos omega t. Why finding out theta A is important? Look at it now from the design perspective. Yeah, what will you gain by trying to figure out what is theta A? When these springs are in action, theta A into A will be the total stretch in the springs, okay, and that will also help you to find out that if this engine is operating at that speed for maybe 5 years, whether the springs will have enough amount of endurance to sustain for so much number of oscillations or not. Okay, all of these are basically the implications of this vibration on the design robustness. Okay.
To summarize this lecture, we had discussed how the design of an undamped vibration absorber is all about and how is that done, what are the parameters required, the condition required. We also understood the importance of mass ratio in the design of vibration absorber, and that part should be kept in mind while designing the vibration absorber, and that itself gives an idea that there are some challenges in the practical implementation of this undamped vibration absorber, which we will try to sort out in the subsequent lecture on tuned mass damper. These are the recall questions that you may try and attempt based on the contents of today's lecture. And these are the answers.